works or anything that we want to talk about? Okay. Well, let's get her done then, huh? So this is going to be the second half of 15.4. So we're just going to kind of continue on with this. So in 15.4, we've been talking about solving exponential and logarithmic equations. What we're going to be introduced in the back half of 15.4, some situations from the real world that can be modeled using exponential and logarithmic equations. So we'll just kind of look at those situations and then do an example problem how we can use that particular model to solve a question. I got I think 4 situations, I think. So the first situation is about sound intensity. So those of you watching, a sporting event, oftentimes, if it's the crowd's getting real riled up and loud, they have the little, the sound meter on the screen. They show how loud it is, and they're like, oh, it's 100 decibels in here. It sounds like a plane taking off, or some nonsense. That's what this first model is kind of doing. It's talking about how we can measure sound intensity. So we measure the level of sound intensity with something called decibels. So our, beta here is the number of decibels. I is the sound intensity measured in watts per meter squared. And then I naught is just some constant. So we can take this model and we can use it to solve story problems that are like living in the real world. So it says, given that the sound intensity of busy city traffic is approximately 10.5 watts per meter squared, what is the measure of busy city traffic in decibels? Boy, that's hard to say. So we're asking for something in decibels. So I know we're going to be using this model that we just went over. And we're told that I naught, we know, is just the constant. I is given to us in the problem, and we're looking for that beta. So we'll just fill in. And then I'll just go to my calculator. You could do this by hand also, but I'm assuming most of us would want to just type this into our calculator. So we get 70 decibels. Woo! Is that a lot? I don't know. Everybody cool? So again, we just have a new model, and we defined what the variables in the model mean, and we just plug some stuff in, right? Okay. Another situation would be earthquakes. So typically we measure the severity of an earthquake with something called the Richter scale. Those of you that are earth sciencers probably already familiar with the Richter scale. And really it's kind of probably in the, the parlance of, your lives. It's, you probably talked about the Richter scale in, middle school science class or something. Feels like somewhere along the way I picked it up. So the Richter scale measurement R, so that we call that the magnitude of an earthquake, can be measured by R equals the log of alpha, that's the amplitude. So by amplitude, you're talking about like how much up and down movement the ground is doing, right? So like ground is here, earthquake happens, ground moves up and down and up and down. We're talking about how much displacement up or down from neutral. That's what we're talking about there with the alpha. The T is the period. So the period is like the amount of time it takes the ground to go from like normal, up, down, back to normal. Just like a sine wave or whatever, right? We'd measure that typically in seconds. And then our last guy is this B at the end, which is just some constant. So the way earthquakes are measured, you have like a machine that measures the earthquake, right? And ideally, we'd want that machine to be right at the epicenter of the earthquake to get the real reading of how severe this earthquake was. Everybody's okay with that? The problem is we can't really predict when and where earthquakes are going to happen. So the machine that we have to measure the earthquake is never really at the earthquake. And what's going to happen is like right where the earthquake is happening, really a lot of shaking going on. But the further you get away from where the earthquake actually happens, the less shaking you're getting, right? So the measurements that we actually make from the earthquake aren't as strong as really the earthquake is right where it's happening. So this factor B that we're adding to the end is like the correction factor for, like our measurement not being like right on top of the earthquake. So that's something we'll find empirically, like you have 5 or 6 different measurements from different locations and you can compare their intent, how big the measurement is and how far it was away. And you get an idea of like, how much should this signal be decreasing as we're getting away from, the epicenter. Does that feel okay, guys? Pretty technical description of what this stuff is, but like you can handle it. All right. Our example says the infamous San Francisco earthquake had a Richter scale magnitude of 7.5. How many times more severe was the most severe earthquake ever recorded? The 1960 Chilean earthquake that had a Richter scale magnitude of 9.5. So when I read this, it's asking me how many times more severe was the most severe earthquake that was ever recorded. So when I read this, I'm like, okay, so I have 2 earthquakes going on here, the San Francisco and the Chilean earthquake. So I'll write 2 different equations here. Everybody's okay with that? Where the R1 is, we're told, is 7.5, and the R2 is 9.5. And what we're really asking for, when we talk about the severity of the earthquake, that's going to be like the more up and down we're getting, the more severe that earthquake's going to be, right? So notice it doesn't ask for the amplitude of the most severe. It asks how much more severe was that amplitude than the San Francisco one. So what we're really asking for is like, what is like the amplitude of the Chilean earthquake divided by the amplitude of the San Francisco earthquake? We might not actually be able to find the number for each of them, but we might be able to find the ratio of like how much more was the one than the other. Everybody's okay with that? So what I'm going to do is I'm going to just take my R2 and subtract my R1 from it. So far, so good. So again, my R2 was 7.5, my R1 was my R2 was 9.5 and my R1 was 7.5, excuse me. Now let's think about these other quantities in here, right? Because it seems like I don't know anything about T1 or T2 or B1 or B2 because I'm trying to find out about A1 and A2. So maybe I'm not worried about filling anything in for those. So let's think about B1 and B2. That's a correction factor based on how far away the instrument that we're using to measure this is, right? But if I'm reporting a magnitude of 9.5, that means that the correction factor is already applied to get to the 9.5, right? Everybody's okay with that? So in essence, the B's are just zeros. They just kind of drop off. Because if I've given a Richter scale measurement, that Richter scale measurement is equivalent to the instrument sitting right on top of the epicenter, that essentially the B should be 0. Because it's already corrected. Does that make sense? It's like saying, I had a test grade of 95 after the curve. What was, what curve would I apply to the 95? Well, 0, it's already been curved, right? It's the same idea with the 9.5. Like, we already curved it. So the curve on it is now 0, right? So if I do that, if I look, I now have the difference of 2 logs, right? So I can use my quotient property of logarithms to condense those 2 logarithms together. So far, so good. Okay. And now 9.5 minus 7.5 is just 2. And to divide fractions, I know we multiply by a reciprocal. Everybody feel okay there? We still got this T1 and T2 going on in here, so let's think about that for a moment. So we live in Michigan. Probably none of us have been in an earthquake before. But you've seen earthquakes on TV or whatever, right? Or on a show or a movie or something, right? This is something that, like, you have some idea of what this would be like. So the ground, T is measuring the amount of time it takes for the ground to go like up, down, and return to normal. Do you think that's going to be a long duration of time or a very, very short duration of time? Probably very short, right? And even if we have a big displacement, it's happening really fast, right? So those T's are probably small enough that even if there's a difference, that difference is kind of negligible. So we're just going to kind of say, close enough. They're close enough to the same value that we're just going to cross them out. Everybody's okay with that reasoning? So now, if I look inside the logarithm, I've got what we want, right? A2 over A1. So, what do I need to do? I need to cancel out that logarithm there. What cancels out a logarithm? An exponent base, right? So I want that exponent base to match the base of my logarithm. What is the base of the logarithm here? Because I don't see a number written. 10 is correct. So we're going to do exponent base 10 to both sides. And I'll write my comically big 10s that you can all snicker at. Those cross out. So I'm ending with the ratio of A2 to A1 being 100. So we can say that Chilean earthquake was 100 times more severe than the San Francisco earthquake. So the takeaway here is that on the Richter scale, each time the Richter scale measurement increases by 1, the severity of the earthquake increases by a factor of 10, right? So if my one earthquake is magnitude 4 and the other earthquake is magnitude 8, the magnitude 8 earthquake is 10 to the 4th, so 10,000 times as severe as the magnitude 4. Emmy? Sure. What do you guys think on that? Is that okay? Earthquakes are scary. I, even though I've lived my whole life in Michigan, have been in an earthquake in Michigan. What? So I used to live for a short time in like the southwest corner of Michigan. And I don't know, it was probably like 15 years ago or something. There was a magnitude 5 earthquake in like northern Illinois. And it hit in the morning, and I remember like laying in my bed and like the building shaking just a little bit, and I'm wondering like, that's weird. And then like a day later hearing that there's an earthquake, and I'm like, oh, it was Saturday morning. That's what I felt. And not, like when it happened, it was so subtle that it wasn't like, I knew something happened, but it wasn't like, like if I wasn't laying down, I don't know that I would have noticed.
Remember when there was a tornado?
Yes.
No, like the one that was
here at Notre Dame.
No, there was.
Sometimes I feel like when Brody walks into community time, it's like there's a tornado. Ha ha ha! Gotcha.
My brother was driving to Chicago and he drove by a foreign tornado. My dad was going 93 to try and get out of it, but was 160.
Yeah.
It was a big tornado.
That's scary. Any more natural disaster stories?
Have you ever seen a tsunami?
No. Have you?
No.
Okay.
They're mostly common in like coastal areas, so California and Japan, because right in between the two of them, there's a lot of seismic.
So you need really an earthquake in the ocean to get a
I was
tsunami.
in New York, and I was like on TikTok. I was in Connecticut, like 30 minutes away from out of New York. I was staying with my aunt a little bit over a year ago. There was an earthquake, like 4 glasses broke, like they shattered on their like what's going on. Huge truck passing that.
Yeah. Yeah.
Have you ever seen what's another acid rain?
Volcanic eruption.
I've never seen a volcano.
I wonder if I've seen
Have you been to Hawaii?
No.
I saw a volcano. It was cool. A lot of smoke. But
Have you ever seen a wildfire?
I mean, I've seen a fire outside.
No, but like a forest fire. Like a.
I've seen a fire in a forest, but not the whole forest on fire.
What about? I don't know. You can keep teaching if you want to. I don't have any more questions.
Okay.
Okay.
Thanks for sharing, everyone. Our next situation, we have, counting this one, 2 more situations. is the pH scale. So those of you that are in a chemistry class or have been in one probably know that pH is a way to measure the strength of acids. Yeah. So our formula, pH, that's our measurement for the strength of our acid, is equal to negative log of the concentration of hydrogen ions inside that particular substance. So our example says that a really sour lemon has a pH of 2.2 and a bottle of bleach has a pH of 10.2. What are the hydrogen ion concentrations of the two? Okay, well, we'll do the lemon first. I'll put a little subscript on that of an L for lemon. So to solve this, what's the first thing I need to do? Not yet, because there's a coefficient in front of it. Yeah, I got to get rid of that negative. I got to move that over. And then we're going to get rid of the log. What do I need to do to both sides to get rid of the log? Exponent base 10. There's my comically big 10s, everyone. Ha 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 ha.
Ha!
Whoa. So I'm left with 10 to the negative 2.2. Everybody feel good there? For the bleach, we set up the same way. Is everybody clear the algebra steps are going to be like identical? Okay, then I'm going to skip the algebra. And then part B says, how many times greater is the hydrogen ion concentration of the bleach than the lemon? That's a typo because there's less ions in the bleach than the lemon. It's probably reverse. So we want lemon over bleach. So when I get that, I get 10 to the 8th. Whoa! It's a lot more ions. What is that? 10 to the 8th is like 100 million times. Woof, guys. Woof. Yeah. All right. Our last situation then has to do with things cooling. So this is Newton's law of cooling. So this refers to, let's see, objects that are cooling down. So we have T of T, that's the current temperature after T minutes, where T is the exponent there. We have the surroundings that the object is sitting in, that's the Tm. We have the initial temperature of the heated object, that's the T naught. And then we have a constant for the specific substance that's cooling. So, who here's ever baked cookies? right? So like you put the cookies in the oven, heats them up to like 350 degrees or something. 450, okay.
350.
I think 350 is probably more likely.
350 as a baker, 350.
Yeah, that's probably right on. So the cookie's now at 350 degrees. Take it out of the oven and you set it on top in your kitchen to cool off, right? So in that situation, the initial temperature of the cookie is 350 degrees. The surrounding, the temperature of the medium is the room temperature in your kitchen, like 70 degrees. And then like 10 minutes later, when you try to eat your cookie, T of 10 would be the temperature of your cookie at 10 minutes. And the K is going to have to do with the rate which cookies cool. Now that's something that like empirically you would calculate, right? Or would look up out of a, like a resource. Another example, maybe you're a medieval blacksmith, right? And you got like your piece of iron in the blast furnace. You heat it up, you pound on it a little bit, and then you stick it into the cold water to do the annealing, right? So like, again, your initial temperature is the temperature of the sword coming out of the oven. The temperature of your medium is the temperature of the cold water you're sticking it in. Your K is specific to iron or whatever the metal you're using to make your sword out of. Or it could even be used for like, you go to the store and you buy some soda pops off the shelf. You come home, what do you do with them? You put them in the refrigerator. So the initial temperature is probably the room temperature for the soda pop. The temperature of the medium, the surroundings, is going to be the temperature of your refrigerator. And the K would be specific to soda pop, right? Like however fast that cools. Probably basically the same as water. But is everybody okay with what we mean by these terms in here? All right. Great. Let's go through and read because the example and try to figure out what's going on here. Because typically the most difficult part of this problem is going to be picking out like what numbers go where, right? So it says a hard-boiled egg is heated to 96 degrees Celsius and placed in a pot of 16 degrees Celsius water to cool. After 4 minutes, the temperature of the egg is 45 degrees. How long will it take in total to cool the egg to a temperature of 20 degrees? So if I look at my temperature or my formula for cooling, what quantity is mentioned nowhere in this story problem? The K, right? Whatever the K for an egg is. So my first step is I have to figure out what K is. I have to find that K. So if I want to find K, I'm going to need a T of T, a Tm, a T naught, and a T. Right? I have to have everything other than K to solve that. Everybody good? Okay. So let's start here. Oops. Hey, come back. There you go. Let's start with the initial temperature, right? You stupid machine. I hate you so much sometimes. You, stop. Okay. What is the initial temperature of the egg going to be? Before any cooling starts, 96. That's right. Okay. And what's the temperature of the medium that we're cooling the egg in? 16. Okay. And do we have a temperature at some time in the future? 45. How far into the future is that temperature for? 4 minutes. So that's my T. Everybody feel good about where we pulled these numbers from? So now let's fill them in to our formula. So we have 45 is equal to 16 plus 96 minus 16, e to the negative k times 4. So far, so good. Now that we've got this set up, we're just going to solve for k. So subtract 16 from both sides. So that's going to be 29. 96 minus 16 is 80. And then we'll divide by 80. Now, I'm not going to convert 29 over 80 to a decimal. I'm just going to leave it as a fraction because it's all going to go in my calculator later anyway. So, like, who cares? Everybody feel okay? Now I got to get rid of that exponent base e. What's going to cancel out that exponent base? A logarithm. Which log base should I use? Not 10. Log base e should match the base of the exponential. And remember, we have a special name for log base e. That's the natural log. And then we'll just divide both sides by -4. For the sake of clarity, I'm going to write that as times -1/4 because I think it's a little bit simpler to get into my calculator if I think about it that way. So -1/4 times natural log 29 over 80. And I get 0.254 thereabouts. So far, so good. Now we're ready to answer the meat of the question. How long in total will it take to cool the egg to 20 degrees? So that's asking me for a little t, right? Yes, sir. Sure. So if I'm going to do that, I'm going to need a t of t, a tm, a t naught, and a k. Feels okay? Now, the t of t is going to be 20 this time, right? That's the temperature we want the egg to cool to. But the Tm, the To, those stay the same, and the K we just found. So now we have everything we need. So we're just going to do this formula one more time. So we'll subtract 16 from both sides. Really the same process as before, right? We'll divide by 80. I recognize that 4 over 80 can reduce, but I don't care because it's all just going to go into my calculator later anyway, so who cares? We do the natural log of both sides to cancel that exponent base of e. And then we multiply by 1 over -0.254, or divide, whatever you want to think about it as. I like to think about it as multiplying by the reciprocal because it's a little bit easier to get it to my calculator correctly. What's up? Yeah.
Yeah, I was gonna say.
So when I finish, I got, it takes about 11.8 minutes. What do you guys think on that? NBD, I hope, right? Now, all you juniors, so this is for the Sunday before we return. I think it's the 27th. That's going to be part of your set. Juniors, or current seniors, you do not need to complete this. This is after your last required assignment for the class, so you do not need to complete these problems. So this is like PS, is it 4 I think we're on? So current seniors though, PS3 is something you're responsible. I think that's like 38 to like 130 though. Yes. And that one is due this Sunday, right? Like the 13th or something. And also you have Delta Math number 1. Probably that's done already though. We worked on that in class one day. But those are the last, or nope. And then we'll also have Delta Math 2 next week, seniors. But those are going to be the last 3 assignments that you're responsible for. Are this PS3, Delta Math 1, and then Delta Math 2 are the last 3 things I'll ask from you guys. Juniors, you have all this and much more. I'm not going to shortchange you guys, you know. And look at this, right on time, 37 minutes or thereabouts. Pretty doggone good.